Hi everyone, and welcome to this next chapter of the Riemann sums, or the limit of the Riemann sums. We're still in discussing notions of the definite integral, and in this video we're going to focus on their properties. In previous videos, we've introduced the definite integral and how it relates to the limit of Riemann sums. So if you recall, performing a limit where the number of subdivisions, the number of subintervals, goes to infinity, allows you to replace the sum of f of xk, the rectangle's heights, and delta x, the rectangle's widths, by the definite integral from a to b of f of x dx. Remember that at this point, only the notation distinguishes these concepts. They actually both represent the exact same thing, which is the act of finding the net area enclosed between a continuous function f and the x-axis within the interval a to b. So in terms of procedure, the integration symbol for now is just aesthetic, because in reality we're still using the limit process to do the calculation. So in this video, we're going to list certain properties of the definite integral that may alleviate, and in certain cases, eliminate calculations that you will agree, in the case of limits of Riemann sums, can be quite tedious. The first property is concerning the sign of the integral. So if a function is non-negative over the interval a to b, then the definite integral from a to b will also be non-negative. This makes sense, since in the case of functions that are positive, or at least non-negative, then the integral calculates the area above the x-axis and below the function. So the outcome will be positive. In the past, we've seen this property regarding summations that allows us to withdraw or to remove any constant multiple from a sum. Just remember that k itself is called the summation index. It is a variable, but anything other than a constant like k, anything else but a variable like k, can be extracted or pulled out. So here c can be removed from the summation. If it's true about sums, it's true about integrals, because keep in mind, integrals are actually summations themselves through the process of Riemann sums. So constant c can be extracted from the definite integral. In the past, we've also seen that summations that act on a sum or a difference of terms can be replaced by individual summations where the operation is maintained but between the summations themselves. If it's true about summations, it will also be true about integrals. And here, this is the addition or subtraction rule. So the definite integral of the sum or difference of two functions can be replaced by the sum or the difference of the individual integrals, maintaining the same bounds. The net area between f and the x-axis for a single x value is always 0. In other words, if the interval used starts and stops at a, which is not super appropriate notation, but I think you get the drift here, then the rectangle's width would actually be 0. And if there is no width, there's no area either. So essentially the property is that an integral calculated from bound A to bound A will always result in a 0 outcome. Mathematically speaking, b minus a over n will always produce the opposite result that a minus b over n will represent. How is that useful? Actually, that means that if you were to replace the order of the bounds, then the definite integral from a to b of f of x will be opposite in sign as the integral from b to a of f of x dx. So this is a property. And there are occasions where we may be tempted to use it if, for instance, the bounds were not presented in the right order, or if an operation has switched their order. The next property we'll discuss is the additive interval property, which states that the definite integral from a to c can be replaced by the integral from a to b, and then the integral and added to the integral from b to c, as long as we maintain the same function as the integrand. Here's a depiction of why this property is actually true. So consider here a region whose net area is being calculated from 0 to 4. So we have a parabola acting as the integrand, and the net area would be the result of the integral from 0 to 4. Well, according to the additive interval property, this net area would be equivalent to the addition of two net areas, the one between 0 and 1, to which we would add the net area between 1 and 4. Now, if the function does not change definition, there doesn't seem to be any reason to use this property. So let's look at a situation where the additive interval property becomes very handy. So here's an example where we'll calculate the definite integral from 0 to 4 of a function that is a piecewise function. And the piecewise function changes rule at 2, which is somewhere between 0 and 4. So on the first portion of the curve, we have actually the upper half of a circle, or the upper half of a semicircle. In the second half, we have a linear function, 2x minus 6, that actually has 3 as its x-intercept. So integrating or performing the integral from 0 to 4 of f of x will actually require we look at this in two pieces because the function's rule has changed. So a good choice here would be to look at two different regions. On the front, we have the integral from 0 to 2, which is the area or the net area under the semicircle or the quarter of a circle. And from 2 to 4, we have the net area located between the x-axis and the line 2x minus 6. So the sum of those two integrals, 0 to 2 and 2 to 4, would be equal to the definite integral from 0 to 4 entirely. Now the area between 0 and 2 is above the x-axis and will reveal a positive number, which is equivalent to the area of the quarter of a circle, so 1/4 pi r squared. As for the definite integral from 2 to 4, well, the signed or the net area is clearly 0 because there is as much area above as there is below the x-axis. So adding up our results, we find a result equal to pi. Notice here that we did not use any Riemann sums simply because the shapes that were involved were geometrically functions or expressions that we knew formulas for. Even and odd functions are not always easy to recognize, but we'll still make a quick mention of properties that involve them. So a function f that is considered even if the function's value at minus x is equal to the function's value at x. Basically, this means that the function would be symmetric across the y-axis. So it's a mirror image with respect to the y-axis. The absolute value function is a good example of that type of function where f at minus 2, for instance, is the same as f at 2. The property states that if a function is even, then the signed area, the net area, or the definite integral from minus a to a of f of x dx will simply be twice the net area, or the definite integral from 0 to a of f of x dx. That's very easy to see in the example we were discussing. So the amount of area in this case, because it's above the axis, under the absolute value function from minus 2 to 2 would be equivalent to 2 times the amount of area between 0 and 2. So this is a property that is only applicable for even functions. A function f is considered odd if the function's value at minus x has an opposite sign to that at x itself. So actually these are examples of functions that have symmetry across the origins. In other words, Notice how the function, in this case, a sine function, has a value at 2, which is of opposite sign to the function's value at -2. Okay, so the function's values are symmetric across the origin. When a function is odd, then integrating over symmetric bounds will always give 0. That's much easier to explain. Again, back to our example on the sine function, then the sine function being an odd function, clearly there will always be as much area below the x-axis as there will be above the x-axis. So the net outcome will be 0.